is the idea behind planar imaging is that with instant X-ray beams, we go through a block of material. Now, eventually, of course, this block is human anatomy because it doesn't really matter whether we're talking about bone in water or real bone in muscle or what have you. It's just easier to talk about things with well-defined geometry so that we can define quantities of interest a lot easier. So up until now, let's just redo a quick review. We said that if I have an instant intensity N0 and I measure this in photons per millimeter squared, right? So this is what we call the fluence. Then, depending on, let's suppose I have blocks of different sizes here, and I'm going to make this, for example, bone, and I could have air doing something else like this, for example. You can see it's beginning to get a lot more complicated, right? So this could be air down here, and then this part in here would be, for example, water, which is H2O. And the X-rays get attenuated with a certain rate given by the linear absorption coefficient, e to the minus mu x, and therefore the number remaining, after traversing a distance x, is going to be given by this. But because of the fact that this might be going through, let's put the air in here, it's inside the material, and this is water. Because of the fact that a given trajectory or ray of photons may actually traverse several different densities or density types, then we replace this with a summation. And we said that N0 or in integral forms becomes e to the minus the integral mu of x dx, and mu is dependent on the medium, right? Depends on medium. Bone, for example, has a very high mu value. Air has a very low mu value. Water has one in between. But it's also interesting that it doesn't depend just on the medium. It also depends on the beam energy, the X-ray energy. And we've seen this because the absorption coefficient can be broken into two parts. It can be broken into the mu photoelectric and plus mu Compton, and this has a strong energy dependence and strong E dependence, and this one has a weak energy dependence, and they don't always overlap. In other words, this is typically in the low energy scale of the X-ray spectrum, and this is in the higher energy scale. This is a weak energy dependence. And so it does depend, even though we like to say mu for bone and mu for air and mu for muscle, it also depends on the beam energy as well. To some extent, it's not as dominant effect as the medium, but it still has some effect on it. Okay, so and also we said that the spectrum of photons are not monoenergetic, but they're produced with a very broad spectrum all the way up to some maximum energy, and these typically go up to, for example, they can go up to 100 keV in photon energy, so it's the energy of the photon, 100 keV, and this is the number of X-rays produced on a target. So it's a very broad spectrum, and it goes up to some maximum amount of X-ray energy, and that they interact either by the photoelectric or the Compton scattering. Okay, so that's where we were, and then of course we have our detector back here, and our detector measures fluence. So the transmitted fluence phi is a function of y. We're going to keep the x direction for the beam direction, and we expect that there would be more absorption in bone than in air, for example. So the highest fluence that penetrates through, and by the way, this is also fluence, so we call this phi sub 0. All right. The highest fluence will be the one going through the least dense material, because it'll have the highest transmission. So I'll get some funny looking curve with that mirrors or reflects the attenuation of the components. And then when I get over into bone, I'm going to get much less, and it'll start off here, and then it'll get less, and then it'll go less, and go like this, right? So this is our fluence, and this is all it basically what it tells us. If we solve this equation in terms of this integral, this is obviously the this is the transmission. This is the fluence phi of y that ends up. And by the way, to make this exactly correct, I should call this mu of xy integrated over x, and then I have fluence as a function of y, which is what we're putting in up here. Okay. And I could, because the physics of the attenuation, this exponential attenuation, is in this integral, then I can also write this as the I can also write this in the signal. This is also called the signal, or the signal intensity, as minus the log of the measured fluence as a function of y divided by phi 0. So this is another way of writing the transmission. And this transmission then will of course be the integral of mu dot dx, mu of x y dx, and this then gives us the what we're actually measuring, right? So when we measure the number of transmitted photons that arrive on our detector in any given interval of space, then any given interval of y, I should say, then what we're really measuring is this quantity right here. Okay? And that's sort of what we left off. And so you can see that a X-ray radiograph only measures fluence. It only measures or the attenuation of fluence. Now the proton radiography is somewhat different than this, and it's going to give us a handle on something a little more interesting for the case of proton therapy. But so we'll start by talking about proton interactions in general. So in order to talk about proton radiography, we have to start like we did with X-rays. You know, how do they interact when they go through tissue? So we'll start with proton interactions, and from that we'll figure out how to generate what we call a radiograph. So proton interactions in matter, right? And the matter that we're interested in is going to be things like this: bone, air, muscle, soft tissue, fat, lung, anything that spans the range of high density to low density is what we're going to be looking at of interest in making a radiograph and trying to discern some information from it. So that's what we have. Okay, so how do they interact? Okay, well, the most fundamental equation, obviously, that I should mention, was given to us by a physicist by the name of Beta, and there's some discussion about this, but I always learned it as the Bethe-Bloch equation, spelled CH at the end. And the Bethe-Bloch equation tells us the following. It says if I send a stream of protons through a block of matter, then they will start out, if they start out with some velocity v and some energy E, and by E I always mean kinetic energy. I'll put a K here for now, but generally we're always talking about kinetic energy when we use the E for a particle. Right? And the results of the beta block equation tell us that the primary interaction that occurs, whether it's bone or air or muscle or fat or whatever, is ionization. In other words, going through this tissue is going to leave a stream of positive and negative ions. Okay? And one of the inherently interesting quantities that we can measure is the rate of energy loss as it passes through matter by this ionization. Now, on an atomic level, we would simply say all we're doing is stripping off valence electrons, and that's true. We'll have protons going through, zipping through matter, and what we're really doing is we're knocking electrons off as it goes through. Gas discharge tubes work the same way. Physics 284 labs with those glass tubes that produce light at different wavelengths, generated by electron beams going through them and creating either excitation or sometimes ionization. So this is the process, and it's a simple enough process. Most of the energy loss occurs via this mechanism. Just as same, by the way, as electrons hitting a tungsten target, right? Most of the energy of the electron goes into ionizing the tungsten, which causes the heating effect, and so that's nothing new. Okay, so to summarize, the equation allows us to express a quantity which we call dE dx, right? And this is the energy loss of the proton, and we usually use units of MeV per centimeter. Right? So to be just what we call a bastardized set of units, because it's not really MKS, it's not CGS, it's not international units. It's units that are convenient for doing calculations. Right? Now, okay. So the beta block equation, what does it tell us? Well, first of all, it does depend on a number of constants. So I'll write out to the most explicit form I can for right now. And what I will do is I'll say that based on the derivation by beta and block, which I also have, which I'll make printouts for you later, that was done by Enrico Fermi in lectures at the University of Chicago, which are also very informative. The equation ends up like this. It goes 4 pi epsilon e to the fourth in the charge of the electron times the electron density, and I'll explain how we get that in just a second, or how we can decompose that into other parts. And then we'll have, for example, the z squared of the projectile. So for our projectile, which is the beam, we have z equals 1. It's the proton, but of equal interest, not necessarily for imaging, but for therapy, is carbon ions, which have z equals 6. And so the rate of energy loss is an important formula for those particles as well. Divided by beta squared. Now beta is going to be the relativistic beta, which is v over c. And this is this is the first part of the expression. And the second part is the following, which is the logarithm of 2me c squared beta squared divided by a quantity called I, which is which is called the mean ionization energy of the material. In other words, every material composed of certain atoms will absorb energy from the beam, and there will be an average energy loss produced by the beam, in order to create that ionization. So this is called the mean ionization potential. Mean ionization potential. And this is potential energy, of course. The energy, or we could think of it as binding energy that holding the electron onto the orbit. And these typically have values in tissues that are between 60 and 90 EV. These are typical values that we see and have found. Okay, so to finishing off this equation, the denominator has a 1 minus beta squared term in it, and minus beta squared. And actually, considering all of the processes that are involved, that is a fairly simple expression, even though it may look not so simple to you right now. We can simplify it further. You can evaluate these constants for z equals 1, for example, and I can evaluate. Let's now look at the most interesting example of materials that we want to examine, and that would be water. We always start with water because our bodies are composed 90% by water, by weight. So using water as our base, we get that the energy loss, dE dx, the rate at which energy is lost in a medium, is equal to, and now we have to evaluate this electron density. So rho E, which by the way I think needs to be expressed a little more better, and rho E is equal to the mass density, rho sub m, so this would be in grams per cubic centimeter, times the z over a, where a is the atomic weight, z is the atomic number, and times Avogadro's number, n sub a. So this gives us the expression for electron density that we can calculate. And we said last time that for water, the effective z for water, or the mean z for water, is around 7.3. Dominated mostly by the oxygen, which is z equals 8, and to some extent lowered by the hydrogen, which is z equals 1. And so this allows us to, the atomic weight A is equal to 18. There's 18 nucleons in the molecule of water. So this allows us to do the calculation. And Avogadro's number is 6.02 times 10 to the 23rd, in case anybody wants to know that. So we have the information now, and let's look at, and if we evaluate this for water, I'm not going to go through all of the components of this, but the end result is that if we're doing this for water, the coefficient becomes much simpler to work with. It's 170 keV. Divided by beta squared times the log of, times the log of the terms that we just came out. 2me c squared, by the way, this would be in terms of electron volts would be 1.02 times 10 to the 6th. So we can put 1.02 times 10 to the 6th in here. We can divide it by the mean ionization for water, which is 75, the mean ionization potential for water, and then we have to put in the energy dependent terms, beta squared times 1 minus beta squared minus beta squared. Okay. Oh, I'm sorry, this should be kV per centimeter. We gotta make sure we have the right units, so this is 170 keV per centimeter. Okay, so that makes it a little bit easier to work with. Furthermore, the range of interest that we're dealing with primarily is for beta between less than 0.6 and greater than 0.1. That's the velocity. So you can see that in the high end range, we are getting into relativistic kinematics. So we have to take into account the mass increase of the proton, for example. And then at the low energy range, we don't have to deal with it hardly at all. Let's see. So this is the range. So there's a very narrow range to really evaluate this over. It's pretty straightforward to do that. And but I want you to see it. Now, what we can do is, the one way that this is often expressed, since we can express the energy in terms of the velocity. So we can have, for example, that the kinetic energy is equal to gamma minus 1 times the mass of the proton times c squared. And this is again the relativistic gamma. So gamma is 1 over the square root of 1 minus beta squared. Gamma varies between 1 and 1.26 for our region of interest. So that's sort of what we have to work with. So we can actually express this in terms of energy, although analytically it's a little messy. But people have graphed this out many times to look at the shape of it. And the shape of the energy loss curve shows us that whether almost regardless of what material we are going through, there's almost a universal shape to it. It does vary slightly, of course, but there are one very interesting, well-defined point on this curve. So this curve is what we would say dE dx as a function of the energy of the proton. And just so I can spread this out a little bit more, I'd like to write this a little bit broader so that I can label some parts to it. This would be something that goes something like this. Let's do it like that. It makes it a little bit easier. This is called the relativistic rise term. It's due to the logarithmic term in here. At very low energies, the energy loss dE dx falls off as 1 over E. So it's rising up very rapidly, and it looks like it goes infinite, of course, when beta as beta goes to 0. But there are physical effects that stop the validity of this equation before we get completely to 0. But for the most part, all the way down till the proton having less than almost a millimeter of travel left, it works pretty well. Okay. So now the area that the interesting part about this is that this is almost like a universal curve, and by universal we can say that that regardless of the species involved here, the species of particles, this minimum occurs at roughly about 3 times m naught times c squared. So 3 times the rest mass of the particle, which in this case is the rest mass of the proton, which is 938 MeV. Now, for reasons that will become clear a little bit, we'll go further. Let's just label this. This is like 2800 MeV, right? It's up here. The region of interest for us, for imaging, where particle accelerators that are used for therapy get their beams, has their energy limited at about 250 MeV. So we're way down here somewhere. So this would be 250 MeV. And they begin there, and what happens is that they lose energy, and as they lose energy, their rate of energy loss gets higher and higher. So if I were to show what happens to a proton beam entering into this block of matter, then here the ddx is relatively low, ddx is low, and then it gets higher and higher. And if it turns out that the block is thick enough so that it actually stops the proton beam, then the maximum ddx will be right near the stopping point of the proton, right when it's lost most of its energy. And I can then draw this in a little slightly different sense. And I'm going to make this the depth in water. Depth in water. And I am going to make this the dose, which by the way is proportional to dE dx. We'll get to the exact definition of dose for charged particles in a moment, but for now we can plot, knowing this curve, the rate at which they're slowing down. We can calculate dE dx as we go along, and we can plot that out as we go deeper and deeper. So we have value dE dx, I multiply by delta x, I lose a little bit of energy, I go to the next point, I say, oh, that's my new energy now because I just lost a little bit. Oh, now I have a higher dE dx, multiplied by delta x, and calculate the amount of energy in that little increment of volume. And if I do that, what I find is that it looks something like this. It rises very, very slowly, and then boom, it goes up. And at the very end, the protons stop. Right? Once they've lost most or all of their energy, their kinetic energy, they stop. They don't go any further. This is called the Bragg peak. Right? This is called the Bragg peak. And this is actually the reason why we use protons in therapy, because if your tumor is right here, for example, you want to give a lower dose where the protons are going in the body, and you want to give the maximum dose in the tumor, which is deep-seated in the body. So this works out very, very nicely for therapy. Furthermore, if you had the spinal cord or the brain stem right here, and that's a no-no to give that any dose at all, then the protons can stop before they reach that critical structure. You cannot do that with an X-ray beam. With an X-ray beam, the dose is always exponentially decreasing, so you're always giving more dose at the entrance relative to here for a given individual beam. Okay? And fortunately, we're not going to talk about that, but that's an important consideration to mention. Okay. So that is a feature of the protons and how they lose energy, and that's sort of what you end up with. Let me take out this other messy part here as well. So this is the Bragg peak. And by the way, while we're on it, this distance from here to the stopping depth is called the range. So I reach the end of range. Usually it typically is defined either at the 50% fall off or sometimes at the 90% fall off, but for us this is so steep, it's usually over only a few millimeters of tissue that it goes from maximum to zero. We'll just call it R for right now. You know, the exact detail of what we call R, not that important. In the Jani tables, by the way, although it's not measured in terms of dose, so I can't really even equivalence of that, so we'll just leave that there. But this is the range R. Now I can define the range R in terms of dE dx. If I want to know, write that explicitly, I can say that the range of protons of a given energy E is given by the integral from the energy E to 0, or we will say E min. We can define E min in a minute, times the integral of dE divided by dE dx. And this is a sloppy physicist's way of showing you that the range in R is dE dx, because d divided by dE dx is just dx. Mathematicians don't like to hear that, but that's the way physicists think about it, right? This is equal to dx. Okay, so that's one way we can do it. And of course, we can express this in terms of beta. I mean, we could also do the integral in terms of beta, right? We could also call this the integral from beta to beta min, because it turns out that it's a little bit more convenient anyway. This would be gamma minus 1 times d gamma. Well, I'd have to convert gamma. Okay, so we'd have to do it over gamma, but f of beta, right? I could express this in terms of beta. I could do the integral over beta, is what I'm saying. because I've already got the function in terms of beta. So probably if I was doing a numerical integration, I would switch to doing the integral over beta, because that's just easier to do that. Okay, so, well, what's also sort of kind of clear from this picture is that, as you would expect, if I have a 250 MeV beam, it's going to travel a greater distance in tissue than if I have a 150 MeV beam. Right? Because a 150 MeV beam, then I'm only starting from this energy, and protons are like bullets going through a beanbag. As they propagate through, they slow down more and more until they stop. And it's called the continuous slowdown approximation. And it works very well to describe things. So if I have, so by the way, we should enter some numbers here, I guess, in terms of, let me try to rephrase this. This one is 150 MeV. Right? This velocity we said was about 0.6 at 250. That's the upper range. The reason we use this, and I'll tell you why in a minute, is that most therapy machines only go to around 250 MeV. This is sort of the upper limit that's available for in proton therapy clinics. It does cost a lot of money to go to higher energies. So unless there's a very strong incentive, we typically don't go over this number to help to keep the cost down. It's the cost of the accelerator and the beam lines and so forth. So anyway, that's sort of down. So at this range right here, we're about 60% the speed of light. So beta is 0.6. At 150, it's about 0.55. So it's slowed down a little bit. But the point is that based on this curve, I would expect, and I find, that I can draw a correlation between the energy of the proton and the range. And people have done that, and the range of interest for therapy are ranges where the proton will travel as little as 3 cm and as high as 250, so this will be the range in centimeters. And this will be range in water. And this range will be, this will go 3 centimeters, and this will be about 37 centimeters. And the curve will go something like this. Okay. And this is the energy at 70 MeV, and this is the energy at 250 MeV. And I get this curve, R versus E, by integrating this function, or 1 over this function. So here's my d dx. This is the integral that I'm going to evaluate. This is d dx of water, and I am going to plug this in and calculate down to close some value of energy close to 0. Now, how close to 0 do we want to go? Clearly, the equation breaks down when beta goes to 0, or I should say the d dx becomes infinite. But typically, what we do as a practical matter is we terminate the minimum energy when the range is less than 1 millimeter. So when R is less than 0.1 centimeter, then we call that, or when R is equal to 0, we call that E min. Right? Because it only has a millimeter of range left to go, and we don't care. You know, we got the answer to within 1 millimeter. We're doing pretty good. Okay. Okay. So that's just a practical way to do the problem and terminate a divergent integral. So this is the curve we get, and that's an important feature. Okay. Now the tables that I handed out to you were the tables written by Jan and I, and turns out we have an extra copy. Oh, did you get a copy? What's that? Turns out that for some reason, the Air Force Weapons Laboratory in Kirtland Air Force Base, New Mexico, was very interested in proton energy loss. I've never studied the exact details of why they were so interested in proton energy loss in muscle, in bone, in lung. Clearly there was some weapons application that we're not familiar of that had to do with radiation, and we don't have to imagine too much more than that. But it turned out to be extremely valuable for the therapy community. And so if you look at these printouts, the first page, for example, will show you the composition of muscle in terms of the elements, and you can read that as well. The energies go from 0.1 MeV up to 1,000, and so let's go to page 3. If we go to page 3, that will be the third page for muscle. And by the way, if we were to look up, for example, water, it would look very similar. The numbers would be very, 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 very close, whether it's dealing with muscle or water. So let me point out a couple. I'm sorry for the quality of the image. It was the best I could do. I tried to optimize the darkness to give you best numbers. Sometimes you have to look at an adjacent number to be able to read it. But considering it was really bad to begin with, I think I did decently well. So let's say, for example, that we look at 200 MeV. Does everyone see that on their page? Mm-hmm. Okay, 200 MeV, look at the third column. The third column is giving me the energy loss in MeV per centimeter. So I can see from that that's looks pretty close to I'm going to say 4.48. But you can also interpolate from 210 and 190 to calculate it. Looks like it's somewhere around 4.48. So the 200 MeV, there's a few things we learned from this. We learned that if the energy of the proton is 200 MeV, which means, by the way, it has a beta that's pretty close to 0.6. So its velocity is 6/10 the speed of light. The rate of energy loss in water is going to be given by dEdx, and that will be given by about 4.48 MeV per centimeter. Okay? So we've learned something from that. We can look up these tables and find out what is the energy loss to any given energy. If we go go to the fifth column, we can also get a number that corresponds to the range. So someone has done this calculation for us. Right? They've integrated the dEdx, 1 over dEdx, from E down to E min, and voila, we get a very nice result out of that. 25.97. So we get that the range of protons in water for 200 MeV is given by, let's call it 26.0 centimeters. Right? 26 centimeters of range in water. So that's also very nice to know. That gives you good information. The other point of interest here that we're going to be interested in is the column towards the end, which is called path length straggling, centimeters. Path length straggling. Okay. So path length straggling has to do with the following, and that is that not all protons are going to make it to 26.0 centimeters. It'll be 26.0 plus or minus. Looking at the path length straggling in centimeters, it looks like it's going to be plus or minus 0.3 cm. Okay? So path length straggling tells us what is the variation from proton to proton. They're not all stopping at exactly the same depth. So the path length straggling then will give us an indication of extra range it may have gone or less than average range it went on a given event. Right? And it's going to be related to what we call in the image, this is the quantity that is going to be related to noise, or what we call statistical fluctuation. Right? One proton goes 26.4 centimeters and the other one goes 25.7. Right? It's there's a statistical range. But the more of those protons that we measure, the better we know the average value. The better we know the average. So we expect that the error is going to, the error in our measurement is going to get smaller by 0.3 centimeters divided by the square root of the number of protons. So this can be used as our measure of noise. So let's see, noise. I think I better go back to erase parts of the board we don't need anymore. So we can write that the noise is equal to the path length straggling per proton path length straggling per proton divided by the square root of the number of protons that are measured in our sample. Okay. So if I measure 100 protons, this error will go down by a factor of 10. Okay. That's the general idea of what we have. Now we can talk a little bit about what is an image. What are we going to? How do we make an image? How are we going to measure it? That sort of thing. Okay. So I'm trying to see if I can include everything up to here now. I think I did. Yes, I did. Okay. So here's how we're going to do it. Look at this. So the way we make a radiograph is with protons. Is we're going to use this property of energy loss, which will be different if it goes through different parts of the anatomy. So, for example, if it goes through a very large thickness of air, for example, it's going to come out with a higher energy than if it went through bone. Right? So, by measuring the energy of the protons on the exit side, here you go, extra handout for you. By measuring the energy of the protons on the exit side, then you can measure a differential in energy, which will be related to variations of density in the body. So, we'll take a simple example. Real anatomy is too hard to work with, so we start with things that we can actually analyze and picture and learn from in simpler geometry. So now we're going to do something similar to what we did before. Let's say, for example, now what I'm going to do is I'm going to put in 2 centimeters of bone. So I'm going to have a block. This is a block of water, right? Well, all this is H2O. And as before, I'm going to make this a 20 centimeter length column of water, but it's got a 2 centimeter thick region of bone. Okay. And by the way, I should point out that, or for reasons that might be a little bit easier, let's call this muscle. Since the tables that I've handed out for you are muscle and bone, so this part is bone. Okay. And I take 200 MeV protons that are coming through here, and let's see, 200 MeV. What I'm going to do is I'm going to calculate the energy of the protons on the back on the back surface on the recording plane. So this will be in my image plane. Right? Just like we did with X-rays. Right? So now what we're going to do is let's calculate what is the energy of a proton that arrives along this trajectory versus the energy of a proton that arrives along this trajectory. Right? And assuming there's a substantial difference, that's going to indicate that I can image, right? Because I want to be able to distinguish regions where protons went through bone or went through air or went through fat or whatever it is. Okay, so how would I go about doing this calculation? Well, I can use, there's a couple ways you could do it, of course. What I can do is I can calculate what's the energy loss up to this point. Right? Let's see, how would I calculate that? Well, I could do the integral. Right? I could do the integral. I'm going to take d dx of muscle. And I'm going to go from 200, dx. I'm going to go from 0 to, and this, if this is 20, and this is in the middle of the phantom, then the first distance to bone is 9, right? So it's 9 centimeters to bone. So I'm going to do 0 to 9 centimeters, and I'm going to do times dx, right? And I can evaluate the integral. I get a value of energy, right? Or energy loss, right? So now I know what the delta x is here. Okay, I subtract that from 200. Right? Now I go through 2 centimeters of bone, and I'm going to do the same thing. I'm going to go 0 to 2, and I've got to have d dx of bone, and I've got to know what the energy is of the protons going through there as well, of course. And then I'm going to calculate this delta E. So this is delta E1, this is delta E2, and then delta E3 will be the last part, right? 0 to 9 cm DE dx of muscle, right? Dx, right? And I can add these up and I subtract them from 200, and that's my energy right here. Right? It's a lot of work. It's a lot of work. Okay, so let's see if there's a faster way of doing it. We'll try to use the range energy these tables that I passed out to you. Well, first of all, what I would do is, how would I use these tables? I would say, well, let's see. The range of the proton to start with through water, it's starting here. It has a range of 26 cm, right? Right? If it goes through 9 cm of water, then the residual range at this point is going to be equal to 26 minus 9, which is, can't do it in my head, 17. Right? So here I say, okay, well, the range of the proton, the energy for which it has, will give it a range of 17 centimeters at this point. Right? What energy is that? Well, let's go back to the range energy tables. Right? So I go back to the range energy tables, and look, I only have muscle, but I said water, and I'm using the interchange. Yeah, you've been using muscle. I said, okay, what is the energy? Well, I got to find out where is the range of 17 on my muscle table. Looks like it's around somewhere between 17, close to 160 MeV. Looks like to me. Maybe it's 158. The number right below it is 15.8. So maybe it's a little bit lower, right? But it's about, let's call it, if it has a range of 17, it's going to have an energy of about 157, I'm going to guess, right? Yeah. More or less, right? So the energy at this point is 157 MeV, right? Okay, now it's going to go through 2 cm of bone. Right. Okay, it goes through 2 cm of bone. So if I go through 2 cm of bone, let's see. Well, let's go to the bone. Let's go to the bone tables. Let's go to the bone tables and let's look up something close to 160. That's the roundest number we have. It's a little bit lower, but if I go to the bone tables, then I may have stapled these in backwards for you, but sorry about that. I'm not sure. What's that? I'm not sure. Anyway, so let's say 160. So 160 MeV. It looks like I've got 9 MeV per centimeter. here, right? So, so the DDX of bone at 160 MeV is 160.
Yeah, 9.02.
Yeah, 9. Let's call it 9. 9 MeV per centimeter. And I could be more precise and say, well, if I go through 2 centimeters, then I'll lose 18 MeV. So maybe using 150 is 160 is a little bit too high. It's actually going to lose, the average energy is going to be closer to 150 because it's going to lose a total of 18, which is roughly a total of 10. So 160 minus 10 is 150. So maybe I should use DDX of 100 and 150, and that's closer to 9.5. Let's just call it 9.5, right? I'm going to round up anyway. It's actually 9.4 on this chart, 9.43, but that's fine. So okay, so now I'm gonna call this 20 MeV. Right? Just rounding up, right? So this is 100. Let's call this 160. So now this coming out here is now 140. What's the energy going to be when it gets to the end? How do we do that? Let's see. So I know I've got 140 MeV. So I've got 140 MeV going through 9 centimeters of tissue of what do we call it? Of muscle. What is E out? What is E out? Okay, so let's. I think I know what you're doing. I think I got an idea. So let me repeat it my words, and then you can tell me whether it's the same thing as what you're saying.
Okay.
The range of muscle at 140 MeV is given by 14, right? As you said, 14, and it has to go through 9. So the residual range coming out here, our residual, is equal to 5 cm of water, right?
Right.
So what beam energy has a residual range, a range of 5 cm? 90, right?
Yeah.
So these tables, I don't have to do any of these calculations. Right? I'm going back and forth between energy and range the whole way. I'm starting out with this energy. I have 26. I know that this energy, it has 26 centimeters of range. If it goes through 9 centimeters of muscle, it's only got 17 centimeters left. I look up the energy for 17 centimeters of muscle. That's my starting energy in going through bone. Now with 2 cm of bone, I don't really, there might be another way of doing it. I could take the full range in bone. I could use the bone tables, but because the delta X was rather small, I just looked up what I thought would be the average DDX between 160 and 140, right? So I calculate that there's a 20 MeV drop across there. So I get from 160 to 140, and I got 9 more centimeters of muscle. So it turns out that this one, 140 MeV, has 14.0 centimeters of range. So after going through 9 cm of muscle, it still has 5 cm of range left. What energy has 5 cm of range?
It's like 70. See, this is where I have a question. It's like 78 MeV, which is different than 89.
Because we did it more accurately. You were doing the estimated, your
Oh.
DDX was estimated here, which was not, it's changing a lot as you go through.
Okay.
And you took it too close to the upstream side, I think, where it just means that your DDX was too low.
Got it. Okay.
Right? So you were doing what I would say is an overly crude estimate. But it's better to go, but do your conversions between energy range, step away all the way down, and then you can just get the final energy right here. Okay. Now the second part should be relatively easy. The second part should be what's the energy after going through 20 centimeters of muscle. Well, it's got 26 to start with, therefore it has 6 cm of range. If I go to 6 cm on the table, then what energy beam has 6 cm of range in muscle?
Roughly 88 or 87.
Probably, I guess is that what you're saying? Is that what you're saying?
Or before I said 89 for a different problem.
1 second. This is muscle. I'm just verifying what you said. You're probably good. I'm just checking. Yeah, you said 80, right? So 1 second. Roughly 90, but it's going to be a little bit less, so I'm going to go with 88 MeV.
Right.
Okay. So there is some change. Obviously, when you only have 2 centimeters of bone and only 1/10 of the entire thickness has changed from one slice to the other, that's not going to be a big difference, but it is detectable. The energy resolution is quite good. It's better than 1%. So you can measure these energies to plus or minus, in this case, 0.8 MeV, roughly. And so this is plus or minus 0.8 MeV. And of course, with higher statistics, this is per proton. With higher statistics, you can get that error down even smaller. You can see a good distinction between those two. Okay, so that takes us part of the way there. We can define our image now in terms of an energy map on the distal edge. So what I can do is say, okay, we've determined that this one is 80, and this one is 88. We said, and MeV. And so one way I can view this. One way I can view my image now is this is an energy map. This is the energy as a function of XY on the plane, right? That's one way to actually make a map, and then I can just add a grayscale to those numbers, and I can get an image, right? It should look similar to an X-ray radiograph by doing that. Now, what's probably more intuitive and what people normally do is they convert this number to what's called water equivalent path length of the material. So we actually use something different, and we'll define that here in a second. It's called the WEPL. And WEPL, by the way, this should be YZ. By the way, I made a mistake here. This should be YZ because we said the beam direction is always in the X direction. Remember? X is this dimension right here. So looking at the image on a plane will be in the YZ direction. Right? Now, the reason we want to do this is that we want to express the image in terms of a quantity that is characteristic of the material that it went through. Okay? You remember, for example, when we did fluence with photons, our image map is phi of YZ. Right? It's our fluence map on the image plane. Or if I took the negative log of that, phi of YZ divided by the incident image intensity, then I would get that this would be equal to the integral of mu of YZ. I'm sorry, mu of XYZ dx. Right? It would be the integral along. So basically, the image, if I expressed it this way, in terms of negative log of this ratio, I would be basically looking at displaying the integral of the linear attenuation coefficient. And that's a property of the material, right? Mostly it's a property of the material. Okay, so we want something like that for protons. So what we do is we define a new quantity which is called WEPL. So what is WEPL and what does it mean? Well, imagine that that the proton beam going through a cubic voxel. So I'll draw a little cubic voxel right here. The proton beam going along the voxel loses amount of energy delta E over an interval delta x. Right? It's given by d dx. Okay. Now what I can do is say what length of water gives the same energy loss delta E over delta X. And I'm going to call that length will be called the wet water equivalent path length. Sometimes it's also called the wet water equivalent thickness. Wet or Webble, right? Well, one is water equivalent path length, the other is water equivalent thickness. Right? Okay, now, mathematically, what I'm doing is I'm saying that the particle that went through some material, which was, we don't know what, bone, air, tissue, or whatever, had a certain rate of energy loss, dE dx. And that d dx will be for that particular medium. Medium, I'll just call it MED. If I multiply that by delta x, that will be equivalent energy loss to going through a different length of water. H2O times delta L. Okay? So I can solve this for delta L and say that delta L is equal to the dE dx of the medium divided by dE dx of water times delta x. Okay? Now, let's suppose that I have a whole column of these voxels that extend from one side of the patient to the other. A whole column of these voxels that the proton is traveling through as it goes. So, for example, if I'm shooting through the head, the eyes are right here, right? So that's my artistic picture of a head. Then I have a trajectory of the proton going through here, and it's going through every voxel. Okay? So I'm going to have an equation like this for every voxel that it goes through. So if I want to know what the total water equivalent path length, Whipple, is, if I want to know what is the water equivalent path length for this trajectory, for this proton, then it's going to be equal to, the Whipple is going to be equal to the summation over all of the voxels in this line of that the patient has been mathematically carved into, and this Whipple is going to be equal to the summation of this ratio of d dx. Now, this ratio of d dx is given a special name. It's called relative stopping power. So this is equal to the RSP times of the voxel, right? Per voxel, per voxel. And by the way, my voxels that are typically ours that we use for imaging, everything's in the millimeter scale. Right? So unless otherwise specified, these voxels are 1 cubic millimeter. How many voxels are there in a human head, 1 cubic millimeter? They're about a few million for a typical head. Typically you can carve up the head of this size into about 3 or 4 million 1 cubic millimeter voxels. That means that you're going to have, in imaging, that's how much information you have for measuring density or characteristics, and you want to know them for every voxel. So this is RSP times delta X, right? And so this is given a very special name, RSP. Relative stopping power, sometimes called proton relative stopping power, because we're always using protons, but RSP means relative stopping power. So if I'm going through a whole row of voxels like this, then the Weppel from here to here, the water equivalent thickness of the head from here to here is going to be the sum of the RSPs over each voxel times the path length through each voxel. And it's going to be I equals 1 to n, where this is voxel number 1 and this is voxel number n. Right? Okay, so this is a very important quantity. We call it the Weppel, right? Water equivalent path length, right? Now let's say that we have a beam that we start off with protons of this energy. It turns out this is a very useful energy for imaging in proton beams because most therapy centers have 200. We could go to 250, but 200 works pretty well. It obviously has to have a range that's longer than the thickness of the head, right? Because you have the detector, you have to have the protons coming out the back side. Right? For therapy, you want the protons to stop in the body, so they will be lower energy because you want them to stop at the location at a given depth. But for imaging, you want them to go all the way through, so you generally need a higher energy beam. Right? Sometimes you don't have the higher energy beam either. That's another limitation. But, for example, 37 centimeters of water will not go through the hips of most adults. So the pelvis cannot be imaged laterally this direction. They can be imaged this way, front to back, but not this way for the typical well, particularly adult males.
But if we use higher energy, can we?
Yeah, if you have, but the therapy, there's very few places with higher energy. So it's very hard to find proton beams above 250 MeV.
But the dose is low even for higher energies.
Yeah, it is, yeah. So anyway, my point is that we want to be able, how do we make this transition, right? So this is the quantity. If I can make a Weppel map, now I have something that expresses the intrinsic quantity of the object that I'm imaging. I'm saying, I know what the water equivalent thickness is of the head through here, through here, through here, through here, through here, everywhere I go through, right? I've basically made a measurement of the integrated density through the patient, okay? And that's a property of the object itself. It's not a property of the beam, right? So this is a pretty useful guy. Okay, so the easy way to get there is to say that the range of the range of protons in water. Let's see. Let's do this one. The range of protons in water for 200 MeV is equal to 26.0 centimeters. Okay, we got that from the Janai tables, and that's equal to the water equivalent thickness of the beam, or the water equivalent. Well, that's equal to the water equivalent path length of a 200 MeV beam. It can only go 26 centimeters. That's the full range. Right? Now, if the protons go through a range with a smaller water equivalent path length through here, and they come out with a residual range in water here, and we'll call this the E residual, then I can write that this quantity, 26 cm, is equal to the Weppel of the phantom, or we'll say the Whipple of the patient. Sometimes we use pieces of plastic that are actually shaped and configured like human parts of the body. You can buy plastic phantoms that are of every part of the anatomy that you want for imaging. If you have enough money, you can buy anything in water, in human-like form. They're amazingly human when you image it. People are shocked at how realistic they look. But this is, you have the Whipple of the patient. That would be this water equivalent path length, plus the residual range in water at the exit, plus our residual, R, whatever right here, range, and this would be the range in water for the residual energy of the beam. And assuming that I measure this quantity right here, which is very possible, I can make a range detector in water or water-like materials that actually measure how far deep they go after they get through the phantom. Then this is what I use for that part of the measurement. Then I can say, okay, now I can convert my residual energy, because here is the residual energy, right? This is the energy residual up here. Right? This is the residual at some YZ value. This is the residual energy at another YZ value. Right? Then I can convert this to Whipple simply by solving this equation for Whipple. And so the Whipple of the patient is equal to 26 centimeters minus my measurement of the residual range in water of the beam with having residual energy be residual. And I can do this two ways. I can either have an energy detector which is calibrated for water range, or I can have a range detector that measures the range directly. This is the simpler way of doing it. If you have an actual range detector after here that measures how far will it go in water before it stops, then it's simply a matter of calculating this difference, and that's your Whipple value. And now you have a Whipple map. Now you have a map of Whipple of YZ. And that's what you want. That's as close as you can get to a expression of the image in terms of the patient anatomy being imaged. The same. So imagine now that the Proton MEV protons go through 10 centimeters of water. Okay? The residual range is going to be 16.1. They're not all going to have the same energy corresponding to 16.1. Some will have a little bit more, and some will have a little bit less. Consequently, the numbers in each of these boxes are all going to be a little bit different. I get A, B, C, D, E, F. They're going to be all a little bit different. How much different? Differ by this amount, delta E. Okay? That's if I do it looking at the map from an energy loss. If I look at it from a Whipple map, which is usually often how we do it, then we will see a similar thing. Right? They won't have the same residual range when they come out of this phantom, even though they all went through the same volume of water, and they all took the same path. Okay? There's going to be a spread. That spread is the noise. It's just like when we talked about X-ray radiographs. With X-ray radiographs, there's a spread of values in here due to the fact that there's a square root of n, sigma of square root of n fluctuation. Even though all of these pixels saw the same fluence coming in, they all went through the same volume of water. There were not the same number of photons that arrived here. Right? Some were a little bit higher and some were a little bit lower. And the amount by which they're higher and lower is square root of n. That's the noise. With proton imaging, the noise is this term right here. It's the energy stripe. So you have to get that from the GENI tables, which a good way to good way to find it. The Jani tables gives you the values in terms of what they call range straggling. So if you look at the Jani tables, there'll be a column here called range straggling versus energy. So you have energy, and you can look up here on the columns, and you'll see that for water equivalent type materials at around 200 MeV, these are about 0.3 centimeters. So the range straggling is plus or minus 0.3 centimeters. So the range is 26.1, but it's plus or minus 0.3 centimeters. Right? That's the noise. Now I can reduce that noise by getting higher statistics. So if I shoot more protons through, this is what I get with 1 proton per voxel. Now there's a problem with doing 1 proton per voxel. Does anybody know what that is? 1 proton. Why do you not want to design an image with 1 proton per voxel? On average, this is the average. This is the total number of protons divided by the total number of voxels.
Is it something to do with randomness and whatnot?
Yes.
So
It has to do with Poisson. Poisson
Oh wait. Okay.
If the average is getting 1 per voxel, what's the probability of getting 0? It's
0. Or no, if the average is 1, what's the probability of getting 0?
It's e to the minus n bar, where n bar is the average number. So I got a 27% chance of having no measurement at all in that voxel.
Oh, yeah, that's
Right?
good.
So let's go to 10 voxels. For 10 voxels, then I get e to the minus 10, and that's about 10 to the minus 4. That's a pretty reasonable, statistic, so that I'm pretty sure that except the numbers greater than 10,000 voxels, up to 10,000 voxels, I'm going to have at least 1 proton to get a measurement, right? But it's also true that if this is a representation of the noise, that this number will go down by the square root of the number of protons in the voxel. Right? Because remember, noise is on a per pixel, because noise is on a per pixel basis. Right? That's the meaning of noise. 2 adjacent pixels will not get the same response, even though they should, because they went through the same material. Right? So there will be now with protons, our map is energy loss or residual range. We can also do. Remember, we can do all those things: residual range or energy loss. We can derive it any way that we want. But the point is that if I want to make this number get smaller, which I can do, then I just have to give it more dose. All right. So that's the gist of it. Right? So that's sort of an overview of, now you can see how Hounsfield units are related to electron density and to Z, and relative stopping power is proportional to electron density also, but it's a function of Z in a different way than dEdx. dEdx depends on the average ionization energy, which is a function of Z. So it's in the logarithmic term as opposed to a stronger dependence that you get with these powers of Z term. It's a much weaker dependence in the beta Bloch equation.
Could you explain the top equation? What are we doing?
Which one? Up here?
Mm-hmm.
Okay, so if I integrate, so if I go through the medium, well, let's see. I'm trying to think of the best way of saying it. If I have 200 MeV, then it has a water. Let's draw it this way. So if I start with 200 MeV and we come out with, we'll say 100 MeV, right? And it goes into the range detector, or the residual range. So this is the, we'll call this either a range or a energy detector. All right? Then this 200 MeV has a range of in water of 26.1. I know this number very well because we use it a lot. And the range for 100 MeV is, say, 7 centimeters. You guys have the range energy table, so you can look it up and tell me what it is, but it should be close to 7. Do we settle with that? Good enough?
Yeah,
Okay.
7's good.
7's good. 7 cm. Okay. So, all right. So that means that what this says is that basically what I'm trying to say is that the range of my incident beam is 26 cm, and if I subtract off the residual range, which I call R residual, which in my drawing, in my particular example, is 7 cm, then I get the Whipple of the phantom, which is whatever that difference is, which is 17, 18, 19.1 cm is equal to 19.1 cm. So maybe this was a bad way of writing it down, but you're right, I probably should not have written it this way, so let me just leave it at this, that, well, let me take this one off too. The water equivalent the residual range in water will be 7 cm, so the Whipple, which is what I want, so remember I'm making a map of Whipple of YZ, is going to be given by this difference. Right? So this is 7 cm measured, this is measured in the detector, measured in the range detector. This is my derived value, right? So, remember also that this 26.1 is 26.1 plus or minus 0.3 centimeters. It's probably less than MeV, but I'm going to write it anyway as the equivalent of 0.3 MeV. And this will be then give me the Whipple, and the Whipple will have a 19.1 cm plus or minus the residual, the range straggling in for 200 MeV is 0.3, so this would be plus or minus 0.3 cm. In other words, this is the error in my measurement. This is the error. And I don't know if this range straggling occurred in the phantom itself or it occurred in the energy detector, but the sum of the two has to add up to 0.3. And therefore, that is the total range uncertainty, because it doesn't really matter whether the range error occurs here or there's a range fluctuation that occurred in the phantom itself. It still adds up to 0.3. But it's 0.3 per proton. Right? So again, to get the noise down, we just have to add more protons.
Okay, so what happened to the Whipple of range detector?
That is, the Whipple, the range detector, is right here. So let's see. This is the this is the Whipple of the range detector. Whipple of the detector. All right. So basically, let me see if I can write it a different way again. The Whipple of the phantom plus the Whipple of the range detector must add up to 26.1 plus or minus 0.3 centimeters. That's what I meant to write. And this is the residual range of the detector if the detector is water equivalent. And if it's not, we have to make a correction for it. But oftentimes the detector itself is water equivalent or very close to it. And so we can think of the residual range in the detector as being the water equivalent path length of the proton in the detector until it's stopped, because the proton's going to range out in here, right? The proton's going to go in here until it's stopped. So if I have a range detector, which would be like slabs of centimeters that are 1 millimeter, thick all the way through, I could measure the last centimeter in which the proton stopped. And if it was water equivalent, then that distance to the stopping edge is the residual range, which is the Whipple of the proton for the detector. So the Whipple in the phantom is the 26.1 minus the Whipple of the detector. The image map needs to reflect the property of the object you're imaging. So it's more intuitive to do it that way if that's the goal, rather than say I could easily just make the energy. I could express this residual energy as a function of y and z. Now, one thing I haven't mentioned is that there are tracking detectors here and here. So I get y and z information here, and I get y and z information here. Right? So the whole assumption here is that I have tracking coordinates that tell me where it went through the phantom. It's easier to conceptualize if you think of it as a parallel beam. So, the simplest thing is to say, well, what if I just look at it this way? If this is my entrance direction, and they mostly go straight, right? Some of them deflect down a little bit, some of them deflect up, most of them go straight through. But in reality, the beam delivery systems are such that the beam is diverging from a point source. And X-rays to some extent too. X-rays have, remember the focal, when you hit the target on the tungsten, the X-rays emanate out in an angular spread from the point where the X-rays are produced. Similarly, the protons are deflected over a region of the target so that you get diverging beams, diverging protons. You have to measure the position of these. And then furthermore, when you make the Whipple map, you have to decide, is my Whipple map going to be at this location, or at this location, or somewhere else? So generally, the Whipple map is taken to be the midplane of the object. This is where we usually make the image. So in other words, you have an XY grid, right? And I measure Whipple in each of these XYs, but if it's a diverging beam, then the Whipple in this XY, if my detector's further down, might end up over here, in this bin. If I make it at the center of the object, it's more consistent, and I always am at the half point between my two measuring stations, which is the best place to actually to actually make it. So furthermore, you know, if you have a YZ position here and a YZ position here, you extrapolate between the two and you find what the YZ is at the point in the midpoint. Once you know the YZ at that point, then you can, when you calculate your Whipple, you put a Whipple value in here. So let's say now what happens is I've got, let's say for each one of these, I've got 100 protons per, I have 100 protons per pixel. Right? And so I'm going to have 100 Whipple values per pixel. Right? What am I going to do with 100 values per pixel? I only want one number for that image, so I take the average. Right? I take the average. So each value going here will be the average. Which pixel or pixel am I going to place it in? I'm going to place it in the pixel that's located at the midplane of the trajectory of the protons going from the front to the back of the object. Okay. So this right here is going to be the imaging plane. That right there, that's going to be the imaging plane. And we'll use that to calculate the image. Now, one important point on all this is that what do you gain by doing a proton image that you don't already have with an X-ray image? What's the point of doing this? I mean, other than the fact that we have a new particle, we can make a new map. Why does it matter? Why does it matter whether, you know, I use a proton or X-rays? Well, the reason is that remember that with an X-ray, when I make an image, what I am really making an image of is the fluids. Right? So in other words, what you're measuring is basically I of YZ divided by I naught. Okay? That's what you're measuring in the X-ray image. So it's basically what you would call the transmitted fluence of fluence. Right? With protons, the fluence is not changing very much. If a proton comes on the input side, it's going to get to the output side. But it does give you an additional information, which is the water equivalent path length through the phantom. Okay. You can say, okay, well, what are you going to do with that information, right? Well, what you're going to do is that you're going to make sure that when a patient gets treated, and if you take an image with a proton, you know, make a proton image, and I get the Whipple map, I want to know that the Whipple map has not changed from one day to the next. Okay. And this is the most direct property of or quantity that tells us where the protons stop in the patient. So this would be a constancy check. Now you can do the same thing. You could do the same thing, but remember that your fluence that you get through here is actually minus the log of I over I0. Okay? So, and that's equal to the integral of mu dot dx. So you have less sensitivity because you're looking for changes in the log of the intensity or the log of the signal, as opposed to looking at changes in the signal itself. So you get a better sensitivity on changes in the patient by doing a proton radiograph map instead of an X-ray radiograph map. So that's the reason for doing that. Of course, you could argue that only 1% of the world's patients get treated with proton, so how important is that? Well, it's pretty important for those 1% that could live or die based on the outcome of the treatment. And if there's an error in where the protons stop, namely that there's an error in the Whipple that you have not accounted for, you haven't measured, then that will allow the protons will stop at the wrong depth. And if that happens, then you will either overdose the patient on normal tissue, or you'll underdose the patient where the tumor is located. Give you an example. So let's say I draw a picture of it, and then we'll stop because we're getting close to the end. We didn't get to the part I was hoping to get to today. But let's say the tumor is located right here, and the proton beam energy, or the energy of the protons, is chosen so that the protons stop, if they're coming this way, they stop at the end of the tumor. So the high dose, there's no dose at downstream, but then it jumps to a high dose, it stays flat, and then it goes low again. So the dose profile versus depth, or versus water equivalent path length, this is the dose versus Whipple. If there's been a change in the Whipple, let's suppose the patient suddenly gets a cold, their sinuses fill up with mucus, the density goes up here. Now, if you don't check it, the protons may stop right here. Right? If the protons stop here because there was a daily change in the density of the patient, and now with mucus in his sinuses, he's got more material there that's going to absorb energy, the protons stop before in a shorter distance than if the mucus was not there. Therefore, that's going to cause a range error. If you make a Whipple map and you confirm that the water equivalent path length from here all the way to the back end of the tumor, if this Whipple has not changed, then if this Whipple is the same every day, then I can be pretty sure that the material density in front of the tumor is the same every day. I mean, there's a pathological case where, for example, this density went down, this density went up. But that's usually not the scenario that happens. It usually happens that if there's been a change in the Whipple, then it's really good evidence that you should at least recheck or re-image the patient and replan them to make sure that the dose being delivered is stopping at the correct edge. This is a daily verification, which one can do, daily verification, and for proton therapy. Or for proton therapy patients. And it's a Whipple constancy check. And it's all based on this, fundamental relation that the Whipple is equal to the integral of RSP of x, y, z integrated over x, px. Right? So that's the kind of background of what we're shooting for.